In this video, we're going to talk about section 3.9 dealing with derivatives of logarithmic and exponential functions. So basically, we'll talk about things like the taking the derivative of a natural log function. And then also we'll be taking the derivative of b to the x. And also we'll take the derivative of functions using what they call the general power rule. It'll be expanded a little bit to include all real powers. And also we'll look at derivatives of the general logarithmic functions as well. And also we'll end it with taking logarithmic differentiation. Okay, so those are the topics that we will look at in section 3.9. Okay, so here we're going to return to the major theme of this chapter, that is developing rules of differentiation for the standard families of functions. We'll first discover how to differentiate the natural logarithmic function. From there, we'll treat general exponential and logarithmic functions. So here we're going to start with the derivative of y equals to the natural log of x. Now, if you remember back in section 1.3, that the natural exponential function, which is f of x equals to e to the x, is a one-to-one function on the interval from negative infinity to infinity. Therefore, it does have an inverse, which is the natural logarithmic function. Of course, that's f inverse of x equaling to ln of x. So the domain of the inverse function is the range of the function f, which is in this case from 0 to infinity. And here the graphs of f and f inverse are symmetric about the line y is equal to x. Okay, so in this case here, this is pretty much the graph of f of x is equal to e to the x. Now, if I was to come up with the inverse of that function, okay, so I know that this point right here is 0, 1. So that means the inverse, I can swap the ordered pairs, it will be 1, 0. So I know the point will be right here. Okay. And of course, that graph also, if I was to draw the line that both the natural log function and the f of x equal to e to the x is, it's going to be this line right here, which I'm going to draw a dotted line for. And that is, of course, y is equal to x. Okay. All right. So the graph is going to look something like this for the natural log of x. It's going to come down here because that interval is going to be from 0 to infinity. And then it's going to go up like this. So that means every point that's on the graph of f of x is equal to e to the x is going to be, it's going to have the mirror image of the points on this graph here, y equal f of x equal to ln of x. And actually, this is what we call f inverse of x. And that is ln of x, by the way. All right, so basically, do be familiar that, of course, f of x equal to e to the x and f inverse of x, which is equal to ln of x, those are inverses, and the symmetric about the graph of the line y is equal to x. All right, so now let's look at some inverse properties for e to the x and ln of x. Inverse properties. In this case here, e to the ln of x is going to be equal to x. In other words, e to the ln of whatever I have for that would be equal to x. And I might need to go ahead and write that in so that y'all can see this a little bit better. Now this is for x is greater than 0. And also ln of e to the x is going to be equal to x for every x. And that's because ln and e are inverses of each other in this case. So here, ln of e to whatever would be equal to whatever, and e to the ln of whatever is equal to whatever. Okay, those are inverses of each other. E and ln are inverses of each other. Now, for y equal ln of x, that's if and only if x is equal to e to the y. Y equals ln of x if and only if x is equal to e to the y. I'm using this notation for if and only if x is equal to e to the y. Because if you think of y is equal to ln of x, that's equivalent to saying log to the base e of x, because ln of x is the same as log to the base e of x. And if I was to convert that into its equivalent exponential form, it would be this: e to the y equals x. Or we can say x is equal to e to the power of y. And then number 3, for all real numbers x and b greater than 0, b to the x is going to be equal to e to the ln of b to the x, which is also the same as e to the x times ln of b. Okay. Those are just a few of the inverse properties of e to the x and ln of x. So I'll go ahead and write this in so that you can see it a little bit better. B to the x equals to e to the ln of b to raised to the x. And that's the same as saying e to the x ln of b. That means you bring the exponent in front of the natural log of b using the power rule. We'll talk about that a little bit later. Okay, on the next page is how we find the derivative of the natural log of x. And it's going to be this: the derivative with respect to x of ln of x is equal to 1 over x. And that is when x is positive. Okay. And also, if you have the derivative with respect to x of the natural log of the absolute value of x, that too will be 1 over x when x is not equal to 0. Because let's say x was negative, we needed that absolute value here because we can take the absolute value of that and it will be positive. So that way we can take the derivative of ln of x, which is, of course, 1 over x. Now, let's say we had a differentiable function. Let's say u is a differentiable at x, and u of x is not equal to 0. That means we can take the derivative with respect to x of ln of the absolute value of x of u of x would be this. It'll be u prime of x divided by u of x. That means we take the derivative of u of x, of ln of u of x, that's going to be 1 over u of x, and then you have to take the inside derivative using the chain rule. For u of x, this derivative will be u prime of x. And we're going to be looking at some examples of just that. Starting with example number 1. And in this case here, we're going to find the derivative with respect to x of 8 times ln of 9x. So in this case here, if we take the derivative of 8 times the natural log of 9x, here we bring the constant that's in front of the ln over. The derivative of ln of 9x, here we follow this rule right here. It's going to be times 1 over ln. No, I'm sorry, 1 over the 9x. And then we have to take the inside derivative here. The derivative of 9x, or the derivative of 9x would just be plain 9. Okay, everyone see what I just did here? All I did here, bring the 8 over, take the derivative of the natural log of 9x, which is 1 over 9x, and then I have to apply the chain rule by taking the derivative of 9x, which is 9. Now let's simplify this a bit. Those 9s will divide out, as you see. And I'll be left with 8 over 1 times 1 over x. This will be just simply 8 over x. And that will be the derivative of 8 times the natural log of 9 with respect to x. Okay. All right, here's the second example, example number 2. Let's say we had this. F of x is equal to 3x to the 5th times the natural log of x. Now here we have to use the product rule because we got 3x to the 5th times the natural log of x. So the way we find that derivative, or f prime of x, now if you want to, you can do this off to the side by saying that the first be 3x to the 5th and the second be ln of x, if that helps. And then find the derivative of the first, f prime. The derivative of 3x to the 5th will be 15x to the 4th. Bring the 5 down, you multiply by 3, you get 15. Copy of the x to the 1 less power. And of course, the derivative of the second, or the derivative of ln of x, is simply 1 over x. And now we can find f prime of x using the product rule. That would be first, which is 3x to the 5th, times the derivative of the second. That's going to be 1 over x, plus the second, which is ln of x, times the derivative of the first. That's 15x to the 4th. All right, and now we can simplify this a bit. I'll bring down this f prime of x notation. But 3x to the 5th times 1 over x. One of the x's will divide out in x to the 5th. You'll be left with an x to the 4th. So in this case here, I will have 3x to the 4th plus that 15x to the 4th. I will put that in front of ln of x. And this will be your derivative for f prime of x, or for f of x. F prime of x, that would be 3x to the 4th plus 15x to the 4th times the natural log of x. Now, they might want this as an answer, or they might want this. They might want you to factor out x to the 4th, if at all possible. And if you factor out the x to the 4th, it will be 3 plus 15 ln of x. So you have x to the 4th times the quantity 3 plus 15 ln of x. Okay? But it all depends upon what my math lab wants as a final answer, and also what your instructor might want as a final answer. When I'm thinking in my math lab, they might want this. Okay. All right, example 3 looks like this. Let's say we want to find the derivative with respect to x of ln of 6x squared plus 7. Well, let's find the derivative of the natural log of 6x squared plus 7. Well, the derivative of the natural log will be 1 over that expression 6x squared plus 7. But then we have to multiply this by our inside derivative using the chain rule. The derivative of 6x squared plus 7 would be this. If we bring the 2 down, multiply by 6, it'll be 12. Copy over the x to the 1 less power. It'll be x to the 1 or just x. And the derivative of 7, well, the derivative of a constant is 0. Okay. Now, the only way we can, all we can do is just simplify this, put the 12x on top, and then 6x squared plus 7 would be in the denominator. So the derivative here would be 12x divided by 6x squared plus 7. Okay. All right, on the next page is finding the derivative with respect to x of the natural log of the absolute value of sine of x. Okay. So using that rule, the derivative of the natural log of sine of x would be 1 over the sine of x. But we got to multiply that by the derivative of sine of x. The derivative of sine of x, that's one of your 6 trigonometric functions here. The derivative of the sine of x would be cosine of x. And this is going to be over 1, by the way. So you might need to go back to section 3.5 and look over those derivatives for those 6 trigonometric functions. All right, so 1 times cosine of x will be cosine of x divided by sine of x times 1 will be sine of x. Now, there's a reciprocal identity that says here, if I do cosine of x divided by the sine of x, I will end up getting the cotangent of x, okay? And that's one of those reciprocal identities that you might need to look up somewhere in one of those calculus textbooks. And I might put a handout on Canvas to let you see what those reciprocal identities are, okay? But do be familiar with those because there's a possibility that you might have to use those and simplify those as a final answer, according to my math lab. Okay, here's example 5. Let's say we want the derivative with respect to x of the natural log of x plus 1 divided by x minus 1. All right, so if I take the derivative of the natural log of this, it's going to be 1 over x plus 1 divided by x minus 1. And then that has to be multiplied by the derivative of x plus 1 divided by x minus 1. In this case, I need to use what they call the quotient rule because I have a numerator and a denominator and I'm taking its derivative. So I need to use the quotient rule. The quotient rule is this. I take the denominator, which is x minus 1, times the derivative of the numerator. The derivative of x plus 1 would just be 1. And then minus the numerator, which is x plus 1, times the derivative of the denominator. The denominator is x minus 1. Its derivative is just going to be 1. All that would be divided by the square of the denominator. Okay. I want to refer back to section 3.4, dealing with the product and the quotient rule, and how that's done, how to take the derivative of that. All right, so let's simplify this. The reciprocal of x plus 1 divided by x minus 1, I just flip this over and it'll just be x minus 1 in the numerator and x plus 1 in the denominator. That 1 over this means the reciprocal of that denominator. Now I'm going to multiply that by 1 times x minus 1 will be x minus 1. Now, the negative will change the sign of every term in the parentheses. So the minus will make the x minus x. The minus will make the plus 1 minus 1. Oh, that's going to be divided by x minus 1 quantity squared. Now we can simplify this by dividing out one of the x minus 1s in the denominator. I'll be left with an x minus 1 in the denominator. Minus x to the minus x adds to 0. So that's gone. And then I'm going to be left with, now I'll do this here, negative 1 minus 1 would be negative 2 divided by, then I get x plus 1 times x minus 1. And I'll go ahead and multiply the x plus 1 times x minus 1. Notice I have a sum and the difference of the same two terms here. So here I can square the first term, which is your x, so the x squared, minus the square of the second term. That's 1. So my derivative will be -2 divided by x squared minus 1. Okay. All right, next example looks like this. Well, we got a trig function here where you need to know what the derivative is going to be. All right, in this case here, let's find the derivative of y with respect to theta. So here we got y is equal to ln of 5 times the cosine raised to the 6 of theta. And I do need to mention here off to the side that 5 times the cosine raised to the 6 of theta. If I was to write that differently, I'll pull the 5 out, and that cosine of theta will be raised to the 6th power. Okay. Now, let's take its derivative here. So here we're going to do dy d theta of this. Ln, the derivative of ln of 5 cosine to the 6 of theta will be 1 over 5 cosine to the 6 of theta. And that's going to be multiplied by, I need to take the derivative of 5 times the cosine to the 6 of theta. Okay, here's what I'm going to do here. Notice I've written it like this, so that way you can see I'm going to bring this exponent of 6 down where the 5 is, so it'll be 6 times 5, which will be 30. And then copy over cosine theta to the 1 less power. So it'll be cosine theta raised to the 5th. And this will be over 1 times the derivative of the cosine. The derivative of the cosine of theta would be, in this case, negative sine of theta. And now let's go ahead and simplify this here. All right, so I know 5 goes into 36 times. I do have cosine theta raised to the 5th, which is the same as cosine to the 5th of theta. That can divide out with 5 of these cosine to the 6 of theta. I'm left with only 1. And that would be 1 cosine to the 1st of theta, or just cosine of theta. Okay. Keep in mind, 5 of these can divide out with these 5, leaving me with a cosine of theta in the denominator. Okay, so if I simplify this a bit, dy d theta would be a negative, and a 6 would be -6 over, and I have cosine theta. Well, actually, I have sine of theta in the numerator, and that's divided by the cosine of theta. Okay, so now dy d theta, that's going to be -6 sine theta over the cosine of theta. That's one of those reciprocal identities. Anytime you have the sine over the cosine, that's equivalent to, say, the tangent of theta. So dy d theta would be -6 times the tangent of theta. Okay. All right. Here's the derivative of b to the x. That's the next thing we'll look at here. The derivative of b to the power of x. So a rule similar to the derivative of e to the x with respect to x equaling to e to the x exists for computing the derivative of b to the power of x where b is greater than 0. And because b to the x is equal to e to the x ln of b by the inverse property number 3, its derivative is going to be this here. Okay, now here they use the chain rule to do this. And noting that e to the x ln of b is equal to b to the x, then we have this theorem right here. the derivative with respect to x of b raised to the x is going to be equal to b to the x times ln of b. Okay. Now, in this case here, I did come up with a proof that shows that the derivative of b raised to the x is equal to b to the x raised to the ln, b to the x times ln of b to ln of b. Okay, so let me go ahead and go through that, the proof of that with you. So here, I want to prove the derivative with respect to x of b to the x is b to the x ln of b. All right, so in this case here, I'm going to let y equal b to the x. I'm letting y equal to b to the x. Now, the best way to get anywhere with this is to take the natural logarithm on both sides. So what I'm going to do here is take the ln of the left side and the ln of the right side. It is an exponential equation, by the way. So to solve an exponential equation, you have to take the natural log on both sides. And also on the right side, I'm going to use the power rule for exponents. I'm going to bring the x in front of the natural log of b. So I'm going to have ln of y equaling to x times the natural log of b. And now I'm going to use what we call implicit differentiation that we talked about in the previous section. So in this case, the derivative of the natural log of y would be 1 over y. And since I'm taking the derivative of y, I have to include dy dx. And that's equal to x times ln of b. Well, ln of b is a constant, so I can bring that down, and the derivative of x will be 1. So I'll have ln of b by itself. Now I need to solve for y. So that y is in the denominator. Well, actually, I need to solve for dy dx. I need to get rid of the 1 over y. What I need to do there is just multiply both sides by y. So this ln of b will be multiplied by y. And what's going to happen here is that the y's divide out. I'm left with just dy dx. So in this case here, dy dx is equal to y times ln of b. But notice what y is equal to. I'll let y equal to b raised to the power of x. So that means I can substitute the y with b to the x. So here b to the x will be equal to, dy dx is equal to b to the x ln of b. Okay, so that's where that derivative is derived from for b to the x. Okay. Not something that I will test you on, but it's good to know where these derivatives come from and how you can prove those. All right, like in example 7, we're going to use that to find dy dx for the function y equals 29 raised to the x power. Okay, so we're going to use that rule there. All right, so if y is equal to 29 to the x, dy dx is going to be this. Here we take that 29 to the x, copy that down, and that's going to be multiplied by the natural log of that base, which is 29. And that's all there is to it. So dy dx is equal to 29 raised to the x times the natural log of 29. Okay. All right, let's look at example 8. Find the derivative of y equals 6 times 5 to the x. So to find dy dx, That 6 is like a constant. I can bring the constant down and take the derivative of 5 to the x. So here I just copy the base down, which is 5 to the x. And then that's going to be multiplied by ln of the base, which is 5. Okay. Now, all I can do there is just simply rearrange some terms here. I can pull this, write down the 6 and pull the ln of 5 in front, and then that'll be multiplied by 5 to the x. That's pretty much all I can do here. Now, keep in mind, I can't multiply the 5 with this 6, because that 5 is with the natural log. Nor can I multiply the 6 with the 5, because that 5 has an exponent of x attached to it. Okay, on the next page is example 9. That's going to be this. Here I want to find the derivative of this function, y equal 11 to the negative x times the sine of x. This we have to use the product rule, because I got 11 to the negative x multiplied by sine of x, so I need to use the product rule. Here's how I use that product rule here. I'm going to let the first be 11 to the negative x, and the second will be sine of x. And in this case, the derivative of the first would be this. That's where I use that derivative for b to the x. That's going to be 11 to the negative x times the ln of the base, which is 11. But then I'm going to take the derivative of negative x. Don't want to leave that out. The derivative of negative x is going to be negative 1. So that means I will have negative 11 to the negative x times the natural log of 11. And then the second is the sine of x, so the derivative of the sine would be the cosine of x. It's the derivative of the second. And now we're going to do dy dx. That will be first, which is 11 to the negative x times the derivative of the second, which is the cosine of x, plus the second, which is sine of x, times the derivative of the first, which came out to be negative 11 raised to the negative x times the natural log of 11. Okay, now if I rewrote 11 to the negative x using positive exponents, this is what I have. The cosine of x will be in the numerator. Then 11 to the negative x, if I pull that in the denominator, it'll be just 11 to the x. And then this negative will make that plus a minus. The sine of x will be in the numerator, times the natural log of 11, that will be in the numerator as well. And that 11 to the negative x, that's going to go in the denominator as 11 to the x. 11 to the positive x. All right. Now you can see here, 11 to the x is the common denominator. The denominators are the same, so I can write that numerator all under a single denominator. So this will be cosine of x minus sine of x, ln of 11, all divided by 11 to the x power. And that would be as far as I can go with that problem. So that's the derivative of y equal 11 to the negative x times the sine of x will be cosine of x minus sine of x, ln of 11, all divided by 11 to the x power. Okay. All right, next we'll look at the general power rule. Now we've been talking about the power rule in previous sections in chapter 3. And as it stands now, the power rule for derivatives says that the derivative of x to the p with respect to x is equal to p times x raised to the p minus 1 for rational powers p. Now we can extend that to include all real powers. So pretty much that rule remains the same, but it's just for all real powers. The derivative with respect to x of x to the p is going to be p times x to the p minus 1. Just simply bring the power down, copy over the x to the power less than 1, to the 1 less power. And if you have a differentiable function like u, a positive differentiable function on this domain, then we apply the chain rule. Here we have the derivative with respect to x of u of x raised to the p. Here we bring the exponent down in front of the u of x function to the 1 less power, and then we take its derivative of u of x, which will be u prime of x. So pretty much we apply the chain rule there. All right, so now let's look at example 10. In this case here, we got y is equal to 5x raised to the 4 pi. Now keep in mind, pi is a constant. It's not a variable. That is a constant. So we're going to apply that power rule here. So to find dy dx, we keep the 5, but we bring down the 4 pi that's in front. 4 pi. Okay. And then copy over the x to the 1 less power. So this should just be 4 pi minus 1. I'm not going to even pull out that calculator to find out what 4 pi minus 1 is. So we'll just leave it as is. But if we just simplify just a little bit here, that 5 times 4 pi would just be 20 pi. And then that will be x raised to the 4 pi minus 1. And I will go no further than that. Okay, so that's how we take the derivative of y equal 5x to the 4 pi. It'll end up being 20 pi times x to the 4 pi minus 1. All right, here's another example of that. This one has a square root in it. Y is equal to x to the square root of 2. And here I want to take the derivative of that. So here, dy dx. The way we do that, since the square root of 2 is a constant, we can bring the constant in front of the x. So we bring down the square root of 2, copy over the x, and then that square root of 2 will be to the 1 less power. And that would just be the following. So that the square root of 2 multiplied by x raised to the square root of 2 minus 1 power. Okay. All right, let's look at the derivatives of general logarithmic functions here. And that's going to be this. If b is greater than 0 and b is not equal to 1, in other words, b is a positive constant other than 1, then the derivative of log to the base b of x will be equal to x 1 over x ln of b, for x is greater than 0. And if you had, let's say, log to the base b of the absolute value of x, its derivative will be 1 over x ln of b for x not equal to 0. Okay, let me go ahead and prove this one as well. All right, so let's say I want to prove this, that the derivative with respect to x of log to the base b of x is going to give you this 1 over x ln of b. And I'm assuming for x is going to be greater than 0, by the way. So here's the proof. I'm going to let y equal log to the base b of x. And then I'm going to use the rule when you convert from logarithmic to exponential form, I can say that b to the power of y is equal to x. So b to the y equals x. And then the next thing I'm going to do here, since it's an exponential equation, I'm going to take the natural log on both sides of this equation. So I'm taking the natural log on both sides of this equation. And on the left side, I'm going to apply the power rule by pulling the y in front of log to the base b. And that's equal to ln of x. Now I'm going to apply implicit differentiation here. Now, b is a positive constant other than 1. So that means that ln of b has to be a constant. So I'm going to bring the constant down, ln of b. Take the derivative of y. That's going to be dy dx. Anytime I take the derivative of y, I have to include dy dx. And by the way, I'm using implicit differentiation on both sides. Now, the derivative of ln of x is simply going to be just 1 over x. And now I need to get dy dx by itself. And to do that, I need to divide both sides by the natural log of b. Or better yet, since I get that fraction on the other side, that 1 over x, it'll be best to take the reciprocal of the natural log of b. That'll be 1 over natural log of b. And that 1 over x will be multiplied by 1 over natural log of b. Yeah, since I'm dealing with a fraction on the other side, the reciprocal of ln of b will be 1 over ln of b. So these ln of b's divide out. I'll have dy dx by itself. So here dy dx is equal to 1 times 1 will be 1, x times ln of b will be x ln of b. Okay, so pretty much I have proven that the derivative of the natural log, the derivative of the log to the base b of x would be 1 over x ln of b. And that's this. Okay, so now let's apply that theorem to example 12. That's going to be this. Y is equal to log to the base 12 of x. And I want its derivative. Okay. So here the derivative of y with respect to x. Using that rule, I'm going to have 1 over. That x comes from the exponent up here. Well, not the exponent. It comes from what we're taking the log of. That's the x. And then we include ln of our base, which is 12. And that's our final answer there. The derivative of y with respect to x of log to the base 12 of x. I'm just following this pattern right here. Bring the 1 down, and that's going to be over. The x is coming from when we're taking the log of, that will be the x, and then copy ln of the base, which is 12. Okay. All right, let's look at example 13. Let's say we had y is equal to sine of 9x times the natural log of sine of 9x, and that's squared, or sine squared of 9x. And here I want to calculate that derivative. And here we must use the product rule, okay? We need to use the product rule here. Let this be the first term, and this be the second. So in this case here, the first would be sine of 9x. The second would be the sine square, ln of sine squared of 9x. ln of the sine squared of 9x. Now let's find the derivative of the first. The derivative of the sine is the cosine, so we have the cosine of 9x times the inside derivative. The derivative of 9x has to be 9. So if I simplify this, this will be 9 cosine 9x. Now for the second, ln of sine squared of 9x. The derivative of that would be this. ln of this is going to be 1 over that sine squared of 9x. Times, now we got to take the derivative of sine squared of 9x. To do that, we take that exponent of 2, bring it in front of the sign, copy the sign over to the 1 less power. It'll be sine to the first, or just sine of 9x. But we're not done yet. We're definitely not done yet. We got to take the derivative of the sine of 9x. The derivative of the sine of 9x has to be cosine 9x. And we're still not done. We need to take the derivative of 9x, which will be 9. So this is where we had to apply the chain rule, not once, not twice, but 3 times. Okay? For that, we had to apply that chain rule 3 times, because you have to do 1 over this and then take its inside derivative, which is going to be 2 sine of 9x. Then you have to take the derivative of sine of 9x, which is the cosine of 9x. And then you have to take the derivative of 9x, which ends up being 9. Now let's simplify this a bit. All right, so that second derivative, the derivative of the second would be this. If I do 2 times the 9, that would give me 18. 1 of the sine of 9x's will divide out. This will divide out with 1 of these. I'm left with the sine of 9x. In the numerator, I'm going to have the cosine of 9x divided by sine of 9x. Because 1 of the sine of 9x's divides out. I'm left with a sine of 9x in the denominator. And I will go no further than that. And I'm going to tell you, and I'm going to show you why. Because when I do dy dx using the product rule, it's going to be this. First times the derivative of the second. The first was the sine of 9x times the derivative of the second, which is 18 cosine 9x divided by sine 9x, plus the second, which is ln sine squared of 9x, times the derivative of the first, which is 9 times cosine 9x. All right, so now dy dx would be this. And the reason why I didn't simplify this, because notice I could divide out sine of 9x altogether. So I'm left with cosine of 18 cosine of 9x plus, and I'm going to pull the 9 in front. Let me see, I can pull the 9 cosine of 9x in front. And then that's going to be multiplied by the natural log of the sine square of 9x. And that would be as far as I can go with that problem. I don't think I can take that any further. Unless I want to factor out 9 cosine of 9x, I could. And then when I do that, factor out the 9 in that 18, that's going to go 2 times. Cosine of 9x is already taken out. I've already factored out 9 cosine of 9x. I'll be left with plus ln sine squared of 9x. Okay. Now, again, it's all going to depend upon what my math lab wants or what your instructor wants for that final answer. Okay. All right, next we'll look at logarithmic differentiation. Logarithmic differentiation. Products, quotients, and powers of functions are usually differentiated using the derivative rules of the same name, and perhaps combined with the chain rule as well. There are times, however, when the direct computation of a derivative is tedious and it can be time-consuming. Like if you had f of x equal to x cubed minus 1 raised to the 4th times the square root of 3x minus 1 divided by x squared plus 4. With something like that, you have to use the quotient rule, the product rule, and chain rules just to find out what f prime of x is going to be. And simplifying it would require additional work, and it can be time-consuming. So now we're going to introduce the properties of logarithms that we talked about back in section 1.3. They are useful in differentiation, in the differentiation of such functions. So these are the 3 properties of logarithms, which were talked about in section 1.3. And pretty much if you've had college algebra, you should be familiar with those 3 different rules: the product rule, the quotient rule, and the power rule. So in this case here, the first one for logarithmic differentiation are this. If you have the natural log of the product, x and y, we can expand that as a sum of the individual logarithms. ln of x times y would be ln of x plus ln of y. We call that the product rule for logarithms. Again, the log of the product is going to be equivalent to the sum of the individual logarithms. And then the second one, if you have the natural log of x divided by y, or the log of the quotient, that's going to be written as the difference of the individual natural logarithms. So this right here is the quotient rule. And then that third one is the power rule. ln of x raised to the y. What we do is pull the power in front of the natural logarithm. So the y times the natural log of x. That's the power rule for logarithms. Okay, again, you should be familiar with these back in section 1.3 or back in college algebra. So we can apply those 3 properties of logarithms to examples like example 14. And in this case here, we're going to use logarithmic differentiation to evaluate f prime of x. Okay, so here we got f of x is equal to x to the x plus 4 raised to the 10th divided by 2x minus 6, that quantity raised to the 8th power. All right, so the first thing I'm going to do here, use a different pen. So in this case, I'm going to write this as y is equal to the quantity x plus 4 raised to the 10th divided by the quantity 2x minus 6 raised to the 8th. This is where I'm going to apply logarithmic differentiation. I'm going to start this off by taking the natural log of both sides of this equation. So here I'm going to do ln of y is equal to ln of that quotient x plus 4 raised to the 10th divided by 2x minus 6 quantity raised to the 8th. Now notice on the right side, let me bring the ln of y down. And that's equal to, now notice on the right side, I have the natural log of the quotient. I have a numerator and a denominator. So I'm going to apply the quotient rule by writing this as the difference of the individual natural logarithms. So the natural log of x plus 4 raised to the 10 divided by 2x minus 6 raised to the 8 would be this, the ln of the quantity x plus 4 raised to the 10 minus the natural log of the quantity 2x minus 6 raised to the 8th. Okay. Now, on the right side, for each of these terms here, on the right side of this equation, I'm going to apply the power rule because I have exponents here. So let me bring down ln of y, and that's equal to, if I apply the power rule, I need to bring the 10 in front of the natural log of the quantity x plus 4. Notice I'm keeping the parentheses around the x plus 4 because I'm taking the natural log of the whole thing. Minus, bring the 8 in front of the natural log of 2x minus 6. Again, the parentheses still remains around the 2x minus 6 as well. And now the next step will be to use implicit differentiation here on each side of the equation. So now, when I take the derivative of ln of y, that's going to be 1 over y. But of course, since I'm taking the derivative of y, I need to include dy dx. Not dy dy, dy dx. All right. And then that's equal to the derivative of 10 times the natural log of x minus 4. Well, I can bring the constant down for the 10. The derivative of ln of x plus 4 will be 1 over x plus 4 times the derivative of x plus 4. That's going to end up being 1. And then minus, bring down the 8, and take the derivative of 2x minus ln of 2x minus 6. That's going to be, in this case, 1 over 2x minus 6, but I need to take the derivative of 2x minus 6. That inside derivative, that's going to end up being 2. All right, so now, let's see if we can simplify this a bit. I'll bring down the 1 over y times dy dx. 10 times 1 over x plus 4 will be 10 over x plus 4. Minus 8 times that 2 will be 16. That's going to be over 2x minus 6. Okay. And I'm going to try to factor out a 2 here in that denominator here. So it'll be 1 over y times dy dx is equal to 10 over x plus 4 minus 16 over, if I factor out the 2 and 2x minus 6, this will give me x minus 3. And here I can divide 2 into the 16. This will go 8 times. Okay. Now what I'm going to do here is get dy dx by itself. I have 1 over y. The reciprocal of 1 over y would just be y. So I'm going to multiply both sides of this equation by y in order to get dy dx by itself. So this will be multiplied by 10 over x plus 4 minus, this will be 8 over x minus 3. And on the left side, you'll see that the y's divide out. You're left with dy dx. Okay, so let me bring this paper up. So here, dy dx would be equal to y times 10 over x plus 4 minus 8 over x minus 3. Now I'm going to replace that y with that x plus 4 raised to the 10 divided by 2x minus 6 raised to the 8. So now dy dx will finally be equal to x plus 4, and that quantity is to the 10, divided by 2x minus 6. The quantity is raised to the 8. And that's going to be multiplied by the 10 over x plus 4 minus 8 over the x minus 3. And that will be my final answer to that problem. I will not take it any further than that. Okay, so that would be the derivative of y with respect to x using logarithmic differentiation. Okay. Okay, let's look at example 15. In this case here, we got, let's say I want to use the properties of logarithms to simplify the following function before computing f prime of x. So here I got f of x equal to ln of 5x plus 6, and their quantities to the 9th power. All right, so let's simplify this. Let's say I want to use, in this case, the product, not the product rule, the power rule, because notice I have an exponent here. I have ln of something raised to a power, so let's use the power rule here. Okay, so use the power rule, where in this case, I'll write it out, ln of x raised to the y equals y times ln of x. So in this case here, I'll bring the 9 in front of ln of 5x plus 6. So I have 9 times the natural log of 5x plus 6. And then we'll take its derivative here. So f prime of x would be this. I bring the constant in front, take the derivative of ln of 5x plus 6. That's going to be 1 over the 5x plus 6, because ln of whatever will be 1 over whatever, times the derivative of 5x plus 6. That's the inside derivative. I have to use the chain rule. The derivative of 5x plus 6 will be 5. And then if I simplify this, f prime of x will end up being, well, do 9 times 5, that will be 45. That will be divided by the 5x plus 6. Okay. So using the properties of logarithms here, I have to apply the power rule to do this and then compute its derivative. So my final answer there will be 45 divided by 5x plus 6, which is what f prime of x will be. Okay, and finally, example 16 is just differentiating. Now notice we got f of x is equal to ln of 5x plus 4 times the quantity x plus 6 raised to the 4th divided by 1 over 2x. That quantity is to the 6th power. All right, it would be best to use those properties of logarithms before you even start to take its derivative. It's easier to do it that way because notice I have an ln of a numerator and a denominator. That means I need to apply the quotient rule first. So ln of this would be expanded as ln of the numerator, which is 5x plus 4 times x plus 6. That quantity is to the 4th. There's a bracket there, minus ln of the denominator. That's 1 minus 2x raised to the 6. Okay, I'm not done yet. I need to apply the product rule here because I got 5x plus 4 times the quantity x plus 6 raised to the 4th. Let's write that as a sum of their individual logarithms. So this will be ln of 5x plus 4 plus the natural log of the quantity x plus 6 raised to the 4th. And then I'm going to bring down minus ln of 1 minus 2x raised to the 6th. Now, on these last two terms here, I'm going to apply the power rule because I have exponents here. All right, that ln of 5x plus 4 is as far as this is going to get. So I'll write that down. Now, for this second term, I'm going to apply the power rule by bringing the 4 in front of ln of x plus 6. Minus, apply the power rule here. I'll pull the 6 in front of ln of 1 minus 2x. Okay. So that is expanded as far as I can possibly get it to be expanded. Now I'm ready to take the derivative. That way I can take the derivative of each and every single term in f of x. So now let's find out what f prime of x is going to be. All right, the derivative of ln of 5x plus 4, that would be 1 over 5x plus 4 times the inside derivative. The derivative of 5x plus 4 would end up being 5, and then plus, bring the 4 down, take the derivative of ln of x plus 6. That would be 1 over x plus 6 times the derivative of x plus 6 will end up being 1. And then minus 6 times the derivative of ln of 1 minus 2x, that's going to be 1 over 1 minus 2x times the inside derivative. The derivative of 1 minus 2x will end up being negative 2. Derivative of 1 is 0. The derivative of negative 2x is negative 2. All right, so now let's go ahead and simplify this, clean this up. 5 times the 1 will be 5, so I have 5 over 5x plus 4. 4 times 1 times the 1 will be 4, so this will be plus 4 over x plus 6. That negative 2 with this minus will make that a plus. A minus 6 times a minus 2 will be a plus, and that'll be 12 over 1 minus 2x. And that will be as far as I can go with that problem. So f prime of x will end up being 5 over 5x plus 4 plus 4 over x plus 6 plus 12 over 1 minus 2x. Okay, so that would be the derivative of that function. So with that, you had to expand by using those 3 properties of logarithms, and then you can take the derivative of each individual piece. Okay, so that concludes this video in section 3.9 dealing with derivatives of logarithmic and exponential functions. Feel free to contact me if you have any questions on any of the problems that were presented in this video or any of the homework problems for section 3.9 found in my math lab.